Hey guys, we are going to take a look at circular motion today. So a quick reminder, acceleration is the rate that the velocity is changing. And remember, an object will accelerate if it slows down, if it speeds up, or if it changes direction. So even if its speed does not change, but it changes direction, it has accelerated. Okay? And this is because velocity is a vector, the magnitude and the direction matter. So changing the direction of an object of a vector is changing the vector. Okay? So from Newton, we know that anytime an object accelerates, there must be an unbalanced force acting on it. So if something is moving around a corner, if a car is going around a corner, for example, it's not changing speed, but it's changing direction. It's accelerating. There must be a force acting on it. Okay? So an object that's changing direction is accelerating, and there must be a force acting on it. So the question is, what direction is the force that's acting on it? So if we have a force and it acts, so imagine this blue car is moving to the right. If I were to push on it from behind, that would make the car speed up. So a force that acts in the direction of the velocity increases the speed. So make sure you think about these. These are conceptual questions you'll see. A force that opposes the velocity. So if I pushed on this car from the right side, then that force opposes the velocity. That will cause the speed to decrease. Okay? But what happens if I push on it in the direction of the red arrow? Well, if I apply a force perpendicular to the velocity, it will not speed it up, it will not slow it down, but it will change its direction. If I continued to act with this force perpendicular to the velocity, so when it's moving this way, I act with a force perpendicular to it. That changes its direction. Now it's moving to the right. I act on it with a force downwards, and that changes its direction. Now it's moving over here. In this direction, I act perpendicular. If a force continues to act perpendicular on a moving object, it'll keep changing direction, and it will move in a circle. Okay? Now, if this force wasn't perpendicular, if maybe it was heading in this direction here, acting on it, then part of that force would cause it to speed up, and part of it would cause it to change directions. And so it would actually move in an ellipse. But we're not going to worry about that right now. We're only going to look at the case where it's perpendicular, which causes it to move in a circle. Okay? So if you've got a rock and you're swinging it around, the rock is moving in this direction at this instant. If the string broke, the rock would continue to move in this direction. That is the path that it would follow because of its inertia. However, if you tug on it with a force that keeps acting perpendicular, you can make it move in a circle. We call this force a centripetal force or a central force. Okay? So forces that act continuously perpendicular to the motion of an object cause it to move in a circle, and we call these centripetal forces. And they always act in the direction of the center of the circle. If you think about a car, here my car is going along this direction, and if there were no forces on it, my car would continue to go upwards like this. However, a force acts on it towards the left, and that causes it to change directions. What force is it that is acting on a car that causes it to change directions? Well, in this case, you say, well, it's a centripetal force acting on the car. But the centripetal force is just the name of it's just the job the force is doing. What force is it that causes the car to move in a circle? So in this case, we would say that it's friction. Because if you imagine this road was icy and there was no friction, this car could not turn in a circle. It would just slide straight up. Okay? So in this case, friction is the force that acts towards the center. So we say that friction is acting as a centripetal force. So a centripetal force is not a new kind of force. Okay? It's the name that's given to our regular forces, like friction or gravity or tension, when it's doing a certain job. All right? So if you go to Frosty Boy and somebody takes your order, they're the cashier, we don't say that a cashier is a new kind of person. The cashier is just Jill, right? It's just a person you already know doing a job. So when somebody says, what is the force making this thing move in a circle, you can't say the centripetal force. That's not a type of force. That's the job it is doing. The type of force in this case is friction, or maybe tension, or maybe gravity. Okay? All right, so to connect with lab, how much force is needed? So to make an object move in a circle, how much force you need depends on the mass of the object. So in lab, I think you found that the force was directly proportional to the mass. It depends on the radius of the circle, how big the circle is. If you have a big circle, you don't need very much force because you're not making it turn very much any given second. So the force is inversely proportional to the radius. And of course, it depends on the velocity. Okay? In fact, I think you found in lab that the force to make something move in a circle was proportional to the velocity squared. There's a simple derivation for the centripetal force. I'm going to skip it right in this lecture, but I will add a link so you can watch me do it on a separate one. It's not required for the AP exam. It's just nice to know where it comes from so you don't think we're just making it up. But here's what you end up with. The centripetal force acting on an object, the force required to make it move in a circle, is equal to the mass of the object times the centripetal acceleration. So according to Newton, F equals m times a. So the force to make something move in a circle is equal to its mass times the acceleration of the object, the rate that its velocity is changing. And that is m times v squared over r. Okay? So the centripetal force is the force it takes to make something move in a circle. In your AP exam reference sheet, which looks something like this, see if I can get it on here. Here's your AP exam reference sheet. If you scroll down, right here it tells you the centripetal acceleration. Okay? So the centripetal acceleration is v squared over r. Of course, the force, F equals ma, so the centripetal force equals the mass times the acceleration, or m, v squared over r. So that's where it is on your reference sheet, okay? All right, and that's the big idea. So let's just solve a couple example problems. How much force would you need if you wanted to make a 0.5 kilogram rock move in a circle? We'll assume the radius is 1.2 meters, and we'll assume the rock is going 5 meters per second. So here is the list of variables. We don't know the centripetal force. We're going to use the centripetal force equals mv squared over r to calculate it, and it turns out to be 10.4 newtons. Okay, that's a fairly straightforward problem. I can't imagine you're going to have much problem with that. Okay. Now, here's a slightly more complicated problem. I've got a brick, and it's on the edge of a merry-go-round. And the merry-go-round has a radius of 1.5 meters. And we don't tell you the velocity. We tell you that the merry-go-round is rotating at 6 revolutions per minute. And so the first thing you got to do is find the velocity. And then once you find the velocity, you can find the force that is needed to keep the merry-go-round, the brick on the merry-go-round. Okay? So let's start by figuring out how fast is this darn brick going. So we know it goes 6 times around every minute. So in 1 minute, which is 60 seconds, it makes 6 revolutions, which is 6 times the circumference. So to find the velocity of the brick, we've got to take the distance it goes divided by the time. If it makes 6 revolutions per minute, that's 6 times the circumference divided by 1 minute. The circumference is 2 pi r. We're going to multiply that by 6. That's the total distance, and the time is 60 seconds. Plug in the numbers, and you get 0.9425 meters per second. Okay, so you can use revolutions per minute and the radius to find the velocity. And once you find the velocity, now you can find out how much force is necessary to keep the brick moving in a circle. Okay, so here we go. The brick is moving in a circle. To find the centripetal force, we take mv squared over r and plug in the numbers, and you get 1.18 newtons. And that force, what is the force that is causing the brick to move in a circle? Well, I think it's friction. You can imagine if the merry-go-round was super slippery, when you started to spin it, the brick would just fly off. So there must be friction that's holding the brick on there. Okay? All right, now there's a misconception alert. People think there's a centrifugal force There is no centrifugal force. It's just an inertial effect. Let me try to explain it like this. I don't really have a diagram to go with it, but can you imagine that if you are sitting in a car and you are going 60 miles an hour and the driver hits the brakes? It feels like you are being thrown forward in the car. It feels like somebody is pushing you forward towards the dashboard. But there is nobody pushing you forward. It is just your inertia. You are going 60 miles an hour. Your body is trying to keep going 60 miles an hour, and the car is trying to stop. And in fact, you need the force of a seatbelt to make you stop also. Otherwise, you would just keep going and skid on the ground and be ejected from the window if there was no force on you. So it feels like somebody's pushing you forward when somebody hits the brakes, but that's not true. If you've ever been on an airplane, you have felt maybe that as the airplane zooms down the runway and takes off, it feels like somebody is pushing you back in your seat. Or maybe if you're in a car and it's accelerating very fast, it feels like somebody's pushing you back. But that's not a force. That's your inertia. You are an object at rest, and your body is trying to stay at rest back there at the beginning of the runway. The seat is pushing you forward. That's why you feel a force on your back, because the seat is pushing you forward, accelerating you along with the rest of the airplane. But it feels like you're being pushed back in your seat, but that's not a force, it's inertia. Likewise, when you are spinning on a merry-go-round, it feels like somebody is pushing you outwards, but that's not really a force. That's your inertia. Your body's trying to go in a straight line, and you need a force pulling on you to keep you moving in a circle. Okay? So there is no centrifugal force. We call it a pseudo-force. It feels like a force, but it's not really a force. Okay? The centripetal force acts inwards. That's what keeps you moving in a circle. All right, let's solve one more example problem. Suppose I have a brick and it's moving on a merry-go-round. The radius is 1.5 meters, and I tell you the coefficient of friction between the brick and the merry-go-round, and I want to know how fast can you spin the merry-go-round so that the brick will stay on. If you spin it too fast, the brick will fly off. So what I'm going to do is draw a free body diagram of the brick. So here's the brick on my merry-go-round, and if you imagine the forces on it, gravity pulls down on the brick with a force of mg, and the merry-go-round pushes up on the brick with a normal force. The tendency of the brick is to slide outwards, and so friction acts inwards. And I'm going to call the direction that friction acts the x direction. Okay? So we can find the friction force. It always equals mu times the normal force. And I think you can see that the normal force, the force going up, must be the same as the force going down here, because it's not accelerating up or downwards. So the normal force is just mg. So the friction force is mu times mg. Okay? Now, if we look at this object in the horizontal direction, it is accelerating because it is moving in a circle. So the forces are not balanced. The net force, which is the friction force, must equal the mass times the acceleration, which is the centripetal force. So the net force, which is the friction force, must equal the mass times the centripetal acceleration, which is v squared over r. So if I set the friction force, mu mg, equal to the centripetal force, mv squared over r, I can then solve that for the velocity, and I get 2.27 meters per second. That is the maximum velocity at which the brick will stay on the merry-go-round. If you go faster than that, then the force that is necessary to keep the brick moving in a circle will exceed the force of friction, and the brick will start to slide. Okay? All right, one last thing. Apparent weight is another way to refer to the normal force. Okay, so sometimes we say, what is the apparent weight? What we're actually asking for is the normal force. Imagine you're on an elevator and you are accelerating upwards. When you accelerate upwards, the force pushing up on you, the normal force, is greater than the force pulling down on you, which is your weight. It has to be bigger in order to accelerate you upwards. This makes you feel like you are heavier because the floor is pushing up on your feet harder. So we call the normal force the apparent weight. And if an object is accelerating upwards or downwards, the apparent weight, the normal force, is not equal to mg. It's different, okay? So we're going to use that in a couple problems. Now, I've got two more examples for you that involve a roller coaster, but I'm going to do those and link them on the homework. So when you get to that problem on the homework, you can watch the video. All right, so right now you're going to go ahead and start the problem set. And when you get down to the problem that involves a roller coaster, there'll be a link to a video so you can watch that and it'll help you with that problem. Okay? Okay, that's the end of this part of the lecture. Go ahead and get going on the problems.